Okay, so we're going to start Unit 2 here. Okay, and in Unit 2, we're going to be looking at a lot of the same kinds of situations that we looked at in Unit 1. So objects that are accelerating, objects that are moving at a constant velocity, okay, things like that. But we're going to be looking at them now from a different perspective. Okay? Rather than just looking at their displacements and their accelerations and their velocities, we're now going to look at what are the forces that are causing the objects to move in this way. Right? So we're going to be looking at situations, again, where the object's traveling at a constant velocity. If something's traveling at a constant velocity, it means that all the forces acting on it are balanced. Okay? If there's any imbalance in the forces acting on an object, the object will accelerate in the direction of the imbalance. So, if you set your cruise on the highway, the cruise control, okay, if you set it, what you're basically doing is you're making the engine balance all the drag forces that are acting on your car. Okay? And then it will maintain a constant speed. Right? So if you're going on a flat highway, your engine doesn't have to work very hard because all it has to do is balance the force of air resistance working against your car as it moves through the air. Okay? And so your engine doesn't work all that hard. As soon as you start going uphill, the engine has to work harder because now there's not just the force of air resistance pushing on your car backwards, but now gravity, or a component of it due to the hill, is also pulling your car backwards. So the car has to now push forwards harder in order to continue to balance those forces. Okay? Now, if you want to speed up, you press the accelerator and your car provides even more force in a forward direction and it accelerates. Okay? It creates an imbalance in the forward direction. Okay? If you suddenly just slam on the brakes, you create a massive imbalance backwards, and your car accelerates backwards. It doesn't keep accelerating because brakes don't work that way, luckily. Okay, you just eventually stop. Okay, luckily friction is not a force that will actually propel you, okay, in a different direction. Okay, well that's not true. Actually, in order to walk, you do actually use friction to propel you. Strange but true. We'll get to that when we talk about Newton's third law. Okay, every action has an equal and opposite reaction. Okay, in order to do what I'm doing right now, I push on the floor, and the floor pushes back on me, okay? And it's only because my feet don't slip that I can push forwards, okay? So I push against the floor backwards, okay? My force is actually backwards. I'm trying to push the earth that way, okay? But luckily the earth is really big, okay? And then the earth, or friction, pushes me forwards. Okay? This is something you can notice about how people walk. Some people push up a lot. Okay? You can see this when they walk across their head. People walk kind of like that, right? Everybody, just now you'll never look at people walking the same way again. Okay, but yeah, some people, they push up a little bit more. So when you actually push up, you're not pushing up, you're pushing down. Yeah, and the floor pushes back up. That's how you jump. Okay? If you want to jump, you actually push down. We never think of that. We always think of it pushing up. But actually, all you're doing is pushing on the floor really hard, and the floor throws you. Physics is so cool. Strange things like that are true. Okay. All right. What we're going to look at today is Newton's first law. Newton's first law is the simplest thing. It's the most obvious thing in the world. Okay? It's not rocket science. It's part of rocket science, but it's not rocket science. Okay? It's super easy. Here's what Newton's first law says. This desk is going to stay right here, provided I don't do anything to it. Well, duh. Of course it's not going to do anything. All the forces acting on it are balanced. Okay? No one's pushing on it, no one's pulling on it. Gravity's pulling on it, but what's preventing it from falling? The floor. Yeah, earth, yeah. Okay? It can't fall through the floor, luckily. Because if it could, we could. Right? So gravity pulls it into the floor, and the floor pushes back up with an equal force, and it stays right there. Okay? Now, if I disturb it a little bit, okay, now it's going to accelerate towards me. Okay? I just created an imbalanced force, so it accelerates. Okay? But if I just pull it at a constant speed, are all the forces still balanced? Yes, they are. Okay? All I'm doing is pulling just hard enough to overcome friction. Okay? Friction's pulling backwards with a certain amount of force. I'm pulling forward with the exact same amount of force, so the desk moves at a constant velocity. Okay? If I push harder than that, then it'll accelerate. We can throw stuff around. All right. So what's meant by inertia? Well, inertia is the one-word definition of Newton's first law. Okay? An object at rest will remain at rest. An object will travel at a constant velocity unless acted upon by an external unbalanced force. That's inertia. Okay? It is the tendency of an object to continue doing what it's already doing in the absence of unbalanced forces. If I'm going to change the inertia of an object, then I have to apply an unbalanced force. That can be a problem. Can something have a lot of inertia? It can. The bigger something is, the more inertia it has. The harder it will be to change that inertia. Okay? When I grabbed that desk, it was easy. Right? I could move it around, push it around. It was really, really easy. The desk's not very heavy. If I go up to a train car and try to do that same thing, I'm not going to have much luck. Because that piddly amount of force that I use to move the desk is not going to do anything to the inertia of the rail car. At least not on Earth, okay, where there's other forces to consider. Okay? Would I be able to move that train car with that amount of force in space? Yeah. Yep. I wouldn't move it very much, okay? But I'd be able to move it. Okay? Things are weightless, not massless, but weightless, okay, in space, and so there's no friction or other things like that to make things difficult for me. And so I would actually be able to move it. But the weird thing would be is if I push on the train car, it pushes back. Now, okay, so I'd get the train car to move away from me at a very small rate of acceleration, and I would move right, away very fast. Okay, it's the same thing happens if I push on the wall, right? If I stand here and I give the wall a big push, okay, what's going to happen? The wall didn't go anywhere. Well, it cracked. You could hear that noise. Okay, but its acceleration was very small, negligible, in fact. Okay, it's much bigger and heavier than me. It has more inertia than me. It's not likely to do anything. Okay, whereas I'm much smaller by comparison. Okay, so if I'm in space and I'm moving around outside of a spaceship, and it's what's called an extravehicular activity, or EVA, is there some dangers presented to me? There are. If I'm not tethered to the spacecraft and I run out of fuel, what happens? I float away. And there is nothing that can be done about it. Okay? If I have no ability to exert an unbalanced force, my inertia will kill me. It'll make me just float away. Okay? Because I can't do anything to change my inertia. I can flap my arms all I want, okay, in outer space. I'll just look panicked, because I will be, but I'll look that way too. Okay? But flailing your arms isn't going to do anything in space. There's nothing to push on. It's not like it does a whole lot on Earth either. Maybe in the water, but not in the air. Okay? So it wouldn't do anything. And my inertia will be that I'll travel at whatever velocity I was moving at when my fuel ran out. Forever. That would be bad. Okay? Probably wouldn't want that. Okay? So it's something to consider. Astronauts really have to be mindful of that, okay, if they are not tethered to their spacecraft. Okay? And there are situations where they would be moving around without a tether, okay? And they would have to monitor their changes in inertia. It happened in The Martian when they were rescuing, I forget his name, Matt Damon, because he always needs rescuing. You ever notice that? Like, other than the Bourne movies, he always needs to be rescued. Saving Private Ryan, The Martian, Interstellar. You always have to rescue him. Anyway, but in the final scene there where they're trying to rescue him and he's launched, but they're really far apart, okay? How does he change his inertia? Yeah, he pricks a hole in his glove, okay, and lets the escaping air act as an exerted force, as a thruster, effectively. He says, I'm going to fly like Iron Man, okay? And he just moves his hand around to vector that force, okay? Now, the likelihood that that would actually be possible and work is incredibly small, okay? And his captain told him that. You'd be using a thrust vector you could barely control. Yeah, as soon as he moves his hand, he's going to go a different direction, okay? So he's got to somehow steer himself with just one hand of escaping air. The other problem is air is escaping. And you need air to not die. Okay? So it would have been a problem. But okay, he found a way to change his inertia. He found a way to exert a force that could move him. And if he didn't do that, he'd have just floated away with whatever inertia the launch had given him.
What would happen if you weren't tethered and sort of floating away? What would happen with like forces around planets?
If you, yeah, so good question. You would be drawn back most likely, depending on how fast you were going. He had already achieved in the Martian escape velocity, right? The whole idea was to launch him really fast. He was going to go faster than any person in history, right? But yeah, so he would have floated away. But then if he'd have come under the gravitational influence of anything else, he'd have been attracted to it. In fact, he probably would have orbited the sun. Okay? Yeah, somewhere out by Mars, he would have orbited, and probably eventually would have been drawn back towards something else. Okay? Yeah, the gravitational influence of something else would eventually draw you in, not soon enough to do any good.
Are there like certain planets that you would like burn up? And if you got like close enough to the atmosphere?
Anyone that has an atmosphere.
Okay.
Yeah. Okay. If it has an atmosphere, you can burn up in it. Okay. That's just friction.
Like how far away from the actual planet do you think it is?
Well, when they re-enter the Earth's atmosphere, it's the very upper part of the atmosphere that they're actually worried about. The atmosphere is very thin, but they're going very fast. Okay? You'd never be able to go as fast as they are in the lower atmosphere. Like you incinerate almost instantly.
Is it possible for something as small as that compared to Earth to get like sucked back into Earth's atmosphere?
Again, you would
die?
and not die. Well, Baumgartner did it.
Falling. Once you get like past like, is there any way of you actually getting back onto Earth before falling to death? If you're just
Yes.
floating and spinning.
I guess the quickest answer is yes. The likelihood of that is slim. Okay, I don't know if anyone saw that Felix Baumgartner, he did the stratosphere jump. So he went out into space on a hot air balloon essentially, right? And then he dove back in. But he had a special suit. He was moving very fast, right? But as the air got thicker, it slowed him down enough that he could open a parachute and survive the rest of the fall. But when you're orbiting, you're going way faster. So that's why he didn't burn up. He wasn't in orbit moving at like 4 kilometers a second. He was just above the Earth. The Earth was spinning under him and he just fell back to it. So he didn't have all that speed that a re-entering spacecraft would have. Does that kind of make sense? All right, so let's have a look here. So first off, we have to define force, because force is everything in this unit. Okay, we're going to talk about forces every single day in this unit. Okay, a force is a push or a pull. Very simple. If you push on something, okay, then you could possibly cause it to accelerate, okay, provided it was unbalanced. Okay, and most of the time it would be. Okay, or you could pull on something. Okay, and remember that an acceleration is any change in velocity. Doesn't have to be going faster or slower. Could be as simple as changing its direction. Okay, that still counts as an acceleration, and it still requires a force. In order to turn your car, friction has to prevent you from sliding in a straight line. Okay, you guys probably noticed it driving in the winter, right? If you take a corner too fast, you don't turn, you just go straight. Okay, that's inertia. Okay, your inertia was you were going straight when the force you were using to turn disappeared. Okay, now there was no net force, and you just continue on in a straight line because there's nothing there. Your inertia is just going to make you do that. It's also, unfortunately, what kills people in car accidents and injures people in car accidents is inertia. Okay? If your car stops suddenly, your inertia is to keep going. Okay? So you're going 100 kilometers an hour and you hit something, your car stops. You continue to move forward at 100 kilometers per hour. That's why you want to wear your seatbelt. Okay? Your seatbelt prevents Newton's first law from helping you exit the vehicle via the windshield usually. Okay? That's not a good way. Yeah, not a good way out of the car. You're better to be in the car. The car is designed to protect you as a safety cage. Okay, airbags, all of that kind of stuff. Airbags don't keep you in the car if you are not seat belted. Okay, they're not that strong. You will just go right over them or through them. Okay, and then through the windshield, and that'll slow you down. The windshield slows you down a little bit. Okay, but yeah, that's not the way you want it. Okay, in a rollover, same thing. Okay, in a rollover, if you are thrown from the vehicle, your inertia propels you in a straight line, which is usually into the path of the rolling car. Okay, because you exit the vehicle usually at the top of the roll. Okay, and you're thrown. Your car is slowing down because of contact with the ground. Okay, you are not, so you fly faster through the air. You land on the ground, and then the car rolls over you. That's usually what kills people on the rollover: being thrown from the car and then having the car roll over them.
So is that like why, like, even if you're seatbelted in, if you have your, like, what are those called? Like the things that block out the sun?
Visor?
Yeah, your visor, if it's like on a slanted angle, why people can still scalp themselves if they're going fast enough and get in a car crash?
Mm-hmm. Yep.
Because you're still moving forward.
You're still
so
moving forward,
it's-
yeah. Yeah. And that's actually now why they designed it.
Yeah, that's why whenever I have my visor, I never keep it on an angle. I always put it like this way, so because you can scalp yourself on it.
Yeah, if it's like this.
Like it'll go like this and then cut back.
Now, most of the time that shouldn't happen because they are padded, right? Like
Yeah.
they're not like.
If you're going fast enough,
Yeah.
it has to happen.
Yeah, and in old school cars, before airbags and things like that, they steering wheels were rigid. They're like really rigid. They were hard, and you could tell someone who got in a car accident and survived because they all had the same scar. Right here, okay? Because they go forward, hit their head on the steering wheel, and the steering wheel would peel their scalp back. Okay? Yeah, they would literally scalp them. Okay? Yeah. Okay? Right there, same scar. They'd have to sew the scalp back on. Okay, right there, okay, in the same place. That's why, after that, but before airbags, they designed steering wheels to collapse. Okay, don't try this, but if you hit your steering wheel really, really hard, it will fold. Okay, it's designed to do that. Okay, to cushion the impact. If you hit it, they're now thicker and padded, obviously. Okay, but if you hit it, it's designed to give. That's, of course, in case your airbag doesn't deploy. Okay, but this is like pre-airbag safety. Okay, obviously your airbag is designed to not let you hit the steering wheel, period. Okay, and steering wheels are also designed with a collapsible column. Okay, so the thing that connects them to the axle that allows you to steer will break. Okay, it'll actually fold and allow the steering wheel and airbag and everything to move forward in a crash because of the force you exert on it when you hit it. Okay, and that's being seatbelted in. Okay, you're still going to hit it hard enough to make the steering wheel collapse. Okay, so that it will move away and not hurt you. Because people, you can have your ribs crushed. Okay, if it doesn't break away. And these are all things obviously they learned the hard way, okay, from watching crash tests and things like that. So cars are designed to be much, much safer, okay, than they used to be. I mean, back in the day, you just had a lap belt, right? You didn't even have something that went across your chest, and it just went across your pelvis. So if you got in a car accident, you could be paralyzed by the force of your body doing this where your head and your feet try to move, okay? And it could actually separate your spine. Okay, so those weren't really good. Plus, they allowed your head to move a lot, okay? And you'd hit the steering wheel and stuff like that. So having the chest strap, the three-point harness, is much safer. Now, I don't know if anyone's been in an accident of sufficient speed, but if you have been, you know that you get this nice rectangular bruise. Okay? Like it's exactly the shape of the seatbelt, okay? Right across your chest. Okay? If you get in an accident, like fast enough usually for the airbags to deploy, you'll get that bruise. Because you usually hit it hard enough. You'll also get bruises on your forearms if you're the driver, okay? Because when the airbag deploys, everyone pictures the airbag like a pillow. It's a punch in the face, okay? Thing detonates. It's an explosion that inflates the airbag. Okay, it's really loud. It's 110 decibels right in front of your face, and it just hits your arms and your hands just fly to the side so that you can go into the airbag.
There's also cars with the back middle seat that just have the one strap around them.
Yeah. And they usually don't get a great safety rating. Because that occupant is usually the one who doesn't do so well. Okay? Like most vehicles will have a three-point harness even in the middle. Like my truck has a three-point harness in the middle. Okay? Most passenger vehicles will have that. It's pretty rare to see that, except maybe in like a half, like the half cab of a truck. If you have like the extended cab, not the crew cab, you might have that. All right. So thing to remember about force. Force is a vector quantity. Okay, when I exert a force, it has magnitude and direction. I push something forward or north, okay, or I pull it backwards or whatever. Force is going to be a vector quantity. Okay, so we do have to remember that as well. Okay, so some forces push, some forces pull. Most of the forces that we're going to deal with the exception of gravity, are contact forces. That means there is either direct or indirect physical contact between the thing exerting the force and the object the force is being exerted on. Okay? Direct would mean you're actually touching it, you're actually pulling or pushing, okay, whichever, okay, on that object. Indirect contact would be, I have a rope, and I'm pulling on the rope, and the rope is pulling on the object. That would be indirect, but it's still a contact force because there's still contact being maintained between the object exerting the force and the object that's moving. Everyone follow me there? Okay. How many directions can a rope exert a force in? One. You can't push on a rope. And if you try it, if you don't believe me, tie a rope to something and then push, and nothing happens. You can coil the rope up into a ball and then go like that, but you can't push on a rope. Because I often have people look right that in a rope and they push on the rope. And can't push on the rope. All right, now, really important thing for this unit, the difference between mass and weight. Okay, mass and weight are different. Okay, this is another problem with society is that we say that they're the same thing and they're not. Okay, someone asks you how much you weigh and you tell them your mass. Okay, your weight is the force of gravity pulling on your mass. It is dependent on the force of gravity to exist. Okay? And it changes all the time, not because you're actually gaining or losing mass, but because gravity is different depending on how far you are from the center of the Earth.
So if someone asked you how much you weigh, what would you actually say?
I would tell them how much in newtons, which would be the force of gravity pulling on my mass. So let's say somewhere around 750 newtons.
How do you count?
I take my mass in kilograms and I multiply by 9.81. Yeah. So the next time someone asks you how much you weigh, tell them that in newtons.
Calculator.
Okay. Well, look it up beforehand. Okay? Look it up beforehand because it's an impolite question, and they should feel awkward about having asked it. If you tell them, because I've done it, okay? You tell somebody how much you weigh in newtons, and they're like, because they think you're weird, and I think they're rude, and so yeah. And I also told the truth. I have lied about my weight. That's my weight. It's a meaningless number to 99% of people. I know.
Does, so you know that you stand on a scale and it
Yeah.
tells you your mass?
Yes.
Is it like sort of lying to us because gravity, like does gravity have to
No, the scale's not lying to you. The scale is calibrated. Okay? I mean, nothing gets called a liar more than the scale. Okay? I mean, but no, it's not lying to you. It's usually calibrated for sea level at the equator, which is actually where you're lightest. Okay? And there's nowhere on Earth you can stand where you'd actually be lighter than at the equator. Okay? Because the Earth is not a perfect circle.
So technically you could be heavier than what your scale is telling you.
Yes.
What if it had scales that like were when you were at the heaviest? Like, is that
It is. But remember, you're always stepping on the same scale, right? You know whether your weight is fluctuating, and that's really what's important, right? We don't want to obsess over our weight. You know, if we're trying to gain or lose, okay, we can track that, but we should never be obsessed about how much do I weigh, because that's not a healthy thing. Unless, of course, you're 700 pounds and you probably need to lose some weight, okay? Because that's not healthy. But I mean, for the vast majority of us, you know, we don't need to worry about that. But no, your scale is calibrated for a certain place, and it may not be telling you exactly what you weigh.
So if I stepped on a scale of say 200 pounds, would I actually be 200 pounds, or would I be more, like, because where the scale's calibrated?
Again, it depends. If you stood on it here, it would depend where it was calibrated for. Now, that I'm saying calibrated. It makes a difference of fractions of a pound. Okay, it's not like, oh, I'm going to weigh 10 pounds more at here than there. No, if you were standing at the North Pole and you stepped on a scale, and then you took that scale to the equator and stepped on it there, it would read a little bit different, marginally different, but not 10 pounds.
Like the saying muscle weighs more than fat, that's actually true, right? That's not something people just say to make themselves feel better.
No, it's true.
Okay.
Because
According to the like BMI index, like the like height thing, like the height and weight, it says I'm like borderline obese. So yeah.
Yeah, that's, I don't put a lot of stock in stuff like that, right? I don't put a lot of stock in that. If I step on the scale and then 2 weeks later I step on the scale and it tells me I'm 5 pounds heavier, I take something out of that. I'm like, ooh, okay, less chicken wings and beer. Okay, more exercise. Yeah, okay, I should probably do that. But I don't let a chart say to me, look, you're 10 pounds overweight. If I feel healthy, I feel okay, then you know what? It's about how I feel about myself. If I can look myself in the mirror, I'm okay. Okay? If I look at myself in the mirror and go, ooh, those jowls are coming back, okay, then maybe I feel self-conscious. But okay, yeah, that's based on so many things,
Yeah, I
right?
feel like they don't take into account that even kids have like a lot of muscle. Like,
Yeah.
they put on muscle.
Well, and at different times in your life too. I mean, like when I was your guys' age, I could eat whatever I want and not gain a pound, right? If I ate like I did when I was in high school now, I put on 3-4 pounds a week. Okay? Your metabolism just slows down, and it sucks. Okay, but it does. It really slows down. And it really starts to slow down when you get to be my age.
Eat more in the summer, I literally actually lose weight because I'm eating more, but my muscle mass I think goes down because I'm not dancing as much. And then as soon as I go back into the winter, I put on more weight again.
You get muscle mass back.
Which is like usually the opposite.
Just hibernation.
Enjoy that while it's Okay, so what is mass then? Well, mass is the amount of matter contained in an object. We measure that in kilograms, okay? So mass is how much of something there is. Weight is the force of gravity pulling on that mass, right? They are two different things. So weight is a force. Mass is a measure of matter, okay? If I go to the moon, I weigh less, but I have the same mass, okay? It's mass that matters, right? Even in space where there's zero gravity, okay, objects may be weightless, but they still have mass, okay? That's why, you know, you don't take barbells, okay, into space on the International Space Station to work out with, okay? It's not that they're weightless. That's actually not the problem. It's that they have mass. And once I get them going, they'll keep going, okay? That's Newton's first law, okay? I accelerate the bar away from myself, which in zero gravity would be a little easier, okay? It still has mass, I still have to push on it. The problem is there's no gravity to stop it. It's very convenient when you're lying on the bench and you do this and the bar doesn't keep going because gravity, okay? But if there's no gravity, off you go. If you don't let go, you're gonna keep flying across the room attached to the barbell, okay? So they're not all that useful. So they use resistance training, like a Bowflex, okay? Something like that, okay, resistance instead, okay? In fact, they have, when they run on the treadmill, because they have a treadmill there and a bike, they bungee cord themselves. Looks like a life preserver that goes around their waist, okay? And they run on the treadmill, bungee corded to the treadmill. Because if they're not, they just hit the treadmill, off they go, okay? So this holds them on the treadmill. But it's because they have mass, thus they have inertia, but they don't have any weight because there's no gravity to pull on.
And another thing that like your heart like decreases in muscle mass and how good it is because it doesn't have to apply as much force to pump blood to your body when you're in space.
Yeah. When we get to Unit 3, we actually have a whole lesson on the effects of zero gravity on the human body, and it's, yeah, there's a lot of really rotten stuff that happens to your body in zero gravity. And it's why people are not allowed to stay on the International Space Station for long periods of time. It's one of the biggest obstacles to getting people to Mars. It's when they get there, how healthy are they going to be? Right? What can we do to keep them healthy? Because the worst thing you could do is get to Mars where you're going to weigh 1/3 of what you weigh here, but you've been in zero gravity so long that your bones and muscles are so weak that you can barely walk around. Okay, so obviously there's a difference in mass between these two objects. There's not a whole lot of matter in the penny, okay? But there's a lot of matter here in the supertanker, okay? There's just more matter, thus there's more mass. Okay? If I apply a force to this penny, I'll accelerate it a lot. If I apply that same force to the supertanker, not so much. Okay? It's mass that matters. Okay. All right. So we've talked about this, mass versus weight. Okay? Weight and mass are two different things. Weight is the force of gravity pulling on your mass. Okay? But as I've said now like 3 times, mass matters. Okay? What's the most important safety feature in your car? Second. That's the second. Okay, airbags are important. Third most important thing. Third or fourth. Well, roll bar is important in terms of not, flipping over, but no one ever thinks of this until I say this. There's a collision. Smart car, semi-truck. Which one do you want to be in? Why? Because it's big. The size of the car. The most important safety feature in your car is mass. Some cars have it and some don't. Okay? I drive a truck. I have kids, and I like knowing that in most collisions I might get into, I'll win. Guys, in every collision, there's a winner and a loser. Okay? And the loser is the one with less mass. Okay? Now, I've been in car crashes a couple of times. Okay? I had a lady who turned left right in front of me. I don't know how she didn't see this coming, but turned left right in front of me, driving like a little Ford Focus. Okay? And we were driving an Expedition, which is the big SUV. And I mean, we just tore through that car like a hot knife.
Easiest way to do it.
Well, I mean, she wasn't moving very fast and was moving across. I was going the speed limit. And when we hit her, okay, our mass was so much greater than hers that we continued to move forward, pushed her through the intersection, okay, and into the lanes past the intersection before we stopped. Her airbags all detonated, and the car was all crumpled. I had to replace the quarter panel and the headlight assembly. No airbags went off because our acceleration was not sufficient to trigger them because we had so much mass. Okay, here's how this works. This is Newton's second law, which we'll get to later. Okay, but force equals mass times acceleration. In a collision, the force experienced by both vehicles is equal. Okay? Even a smart car and a semi-truck hitting each other, the force exerted on each vehicle is identical. What's different is the acceleration, because if I isolate acceleration, it is dependent on the force, which is the same for both vehicles, and the mass of the vehicle. So the bigger this mass is, the smaller the acceleration experienced. That's why mass matters in a collision. The bigger vehicle experiences less acceleration. It's usually the one that continues to move forwards. Okay? Yes, I'm going to slow down and eventually come to a stop because we hit the brakes, but also because I'm bigger, okay? I'm going to keep moving forward. The car that loses is the one that goes backwards. Their velocity changes from positive to negative. Okay? Mine changes from positive to 0. Win. Okay? That's what you want.
How fast are you going?
60 kilometers. She was okay, yeah, she got out, she was fine. But I mean, all her airbags had gone off and all of that. Like, at 60 kilometers an hour against a stationary object, essentially stationary because she was turning, is not a huge collision, right? It was enough given she had a small mass, we had a lot of inertia, we had a lot of momentum too because we were moving, okay? But in the end, not enough usually to hurt anybody seriously, okay? Now, had she been going 60 in the opposite direction, okay, that could have made a difference. Okay? She'd have had more momentum. Wouldn't have changed the fact that we'd still win. Okay? We still have more mass. Our acceleration would be less.
I should probably ask your chemistry major. Do you know what sets off, like what explosion that is?
Yes, it's sodium azide. I can't remember what the formula is, but when it's detonated, it fills the bag with oxygen. Or nitrogen, I can't remember which. That's Na3N, it's nitrogen. Pops, yeah, it just inflates really, really quickly. The reaction releases nitrogen really fast, or whatever the gas is. It releases it really fast. Okay, because it couldn't be a harmful gas, because obviously it escapes, right? The airbag does not stay inflated either. People have this vision. When the airbag goes off, you just sit there on the, no, it actually, it's full of holes, and it just inflates so fast and then deflates slowly. Otherwise, it'd be hard to get people out of the vehicle after. All right. Okay, so understanding Newton's first law, okay, if we think of like hockey or like paint drying, not paint drying, curling, that other boring thing. Okay, those are good examples of Newton's first law. Okay, if the ice is frictionless and you get something sliding on it, it should slide forever. Okay, provided you have a long enough, forever piece of ice. Okay, but if it's frictionless, there's nothing to slow it down. There's no unbalanced forces. Okay, the reality is that there are unbalanced forces, okay, and they do eventually slow down. There's even a small amount of friction on the acting on the puck. Okay, everybody with me there? Okay. So what we're going to look at probably tomorrow, yeah, okay, is that we're going to look at some videos on Newton's first law, some good physics, bad physics kind of stuff. We're also going to look at a few crash tests. Okay, running some cars through their paces and crash tests and seeing what happens there. Okay, in terms of Newton's first law.